In this video, we'll look at stoichiometry involving solutions, including looking at how to do dilutions. Before we begin, let's review molarity. Remember, molarity is defined as the number of moles of solute per liter of solution. So when we look at our molarity, that's our moles of solute divided by our liters. Or shorthand, we tend to write out moles per liters. And remember, to make a solution of a specific molarity, you usually have to put the solute in the flask, then you add the water to the desired volume. Since most solutions are stored in a concentrated form because it takes up less space, those are called our stock solutions. Stock solutions must then be diluted to the appropriate concentration before you can do a reaction. So many lab procedures call for a less concentrated solution to be used. That means the stock solution must then be diluted. And to determine how much of the stock solution to use, we use our dilution equation, M1V1 equals M2V2, where M1 and V1 come from the stock solution, they're the more concentrated one, and M2V2 are our final diluted volume and diluted concentration. Now, some people ask, how do we know that this equation can actually work? If we think about it, M1V1 is moles over liters times liters equals our second one, moles over liters times liters. So you can see the liters would cancel out and it's just the moles equal moles. So this means when we do a dilution, the number of moles of our solution stays the same. We don't actually change the number of moles. Instead, we're just changing the concentration of those moles. We can think about it as if we start with a beaker with a small volume that contains 5 molecules of our desired solute. We then do a dilution by adding water. So when we look at the final volume, it's now much higher. But since we didn't add any extra solute, we still just have those 5 molecules floating around. They just have a lot more space now. So we can use this very handy equation, M1V1 equals M2V2, to figure out what the new volume is and what the new concentration would be very quickly. But remember, when we do this, the number of moles will always stay the same. We don't change the number of moles when you do a dilution. So let's practice this idea with these calculations. So let's practice. If we prepare a 5-liter solution of a 1.5 mole potassium chloride solution from the stock solution of 12 molars, how much of the stock solution do we actually need? We're given the final volume, the final concentration, and the initial concentration. So if we look at our different ones here, the 5 liters, that's V2. The 1.5 mole, that's M2. The stock solution, the 12.0 molar, that's M1. So you can see the only thing we don't know is V1. So we're trying to figure out what V1 is. So we can use our equation, M1V1 equals M2V2 to set it up. And then this equation can be rearranged to figure out V1 equals M2V2 over M1. And then once we plug in all of our numbers, we get 1.5 moles per liter times that 5 liters divided by 12.0 molar. And then when we do this calculation, we find that V1 equals 0.625 liters. So what this means is I would need 0.625 liters of my stock solution and dilute it up to 5 liters in order to prepare that 1.5 molar concentration. So we can also use the idea of molarity to figure out what the concentration of different ions are in solution. An example of this, if we have 1.5 molar concentration of sodium phosphate, what is the molar concentration of the sodium ions? What is the molar concentration of the phosphate ions? So if we remember, if I have sodium phosphate, I have 3 sodiums and 1 phosphate. So when that gets dissolved in solution, we have 3 sodium ions plus 1 phosphate ion. So if we want to figure out what the molarity is of the sodium ions, I would simply take my 1.5 molar and multiply it by 3 because I have 3 of them in solution. For the phosphate, since I only have 1 phosphate, that's going to equal that 1.5 molar. So that means if we look at our answers, the molarity of the sodium ions is 3 times that 1.5 molar, which equals 4.5. The molarity of the phosphate ions is just going to be that 1.5 molar. And this makes sense because if we take a sodium phosphate, it does break up into 4 different ions. And each ion would have its own concentration. Now that we've looked a little bit at dilutions, let's look at solution stoichiometry. When we do solution stoichiometry, it generally follows the roadmap here, where you have a volume A, you determine the moles A, use the balance equation to convert to moles of B, and then use the molarity to convert to volume of B. So we'd use molarity of A, our balance equation, and molarity of B. So in reactions that involve aqueous reactants and products, it's often much more convenient to determine the amount of reactant or product in terms of its volume and concentration. It's usually a lot easier to figure it out in terms of its molarity. And so we can use this fact to calculate the number of moles of reactant or product by using the molarity. And we can use the balance equation to go between different reactants or go between reactant and product. Let's practice this. If we have a 0.125 molar solution of sodium hydroxide, how much of it do we need to completely neutralize a 0.225 liter solution of a 0.175 molar sulfuric acid solution? When we start with a question like this, the first thing we need to do is write a good balanced reaction. Once we have a balanced reaction, then we can worry about the calculations. With our balanced reaction, we know we need 2 sodium hydroxides for every 1 sulfuric acid. So then looking at this, I can also see I have a molarity and I have another molarity, and I have the liters to start with. So I'd start with my liters of sulfuric acid, use the molarity to convert into moles of sulfuric acid, then use the coefficients from the balanced equation to convert between moles of sulfuric acid to moles of sodium hydroxide. Once I'm in moles of sodium hydroxide, I'll use that concentration to convert to liters of sodium hydroxide, which gives us 0.63 liters of sodium hydroxide is needed to neutralize that 0.225 liters of sulfuric acid. So you can see the liters of sulfuric acid cancel out, the moles of sulfuric acid cancel out, then the moles of sodium hydroxide cancel out, leaving you in just liters of sodium hydroxide. With questions like these, it's important to write out all of the units, including the chemical that is associated with that unit. So remember, whenever we do solution chemistry and solution stoichiometry, It follows the same guidelines and the same pattern that we did for the regular stoichiometry when we learned how to go from grams into grams. Now we're just doing liters to liters. So you're going to start with liters of one compound, use the molarity of that to convert to moles, balanced equation convert into moles of the second compound, then use the molarity of the second compound to convert into liters. But you can see it has exact same setup and exact same steps to do as when we did our grams to grams. Now you all should be able to do solution stoichiometry and convert between liters and moles of different reactants or of reactants to products.